Hello. It's my pleasure to introduce Christine Berkesch from University of Minnesota. She is going to talk about multigraded modules.
All right. Okay. Thank you so much. Welcome again. Well, welcome to me, I guess. You've been here, but I'm excited to welcome you to this class. I'm at University of Minnesota. I've been there now since 2013. I came to the Fields Institute for my very first summer school and research conference way back, a long time ago. I won't tell you what year. No, I will. It was 2006. It was a Macaulay II school and meeting. It was really fun. So I got 2 weeks at Fields then and just had a blast. I hope you all are having fun, and I'm excited to get to spend time with you this afternoon. So I'm going to tell you some things. Please interrupt me as much as you'd like to ask questions. And then I have the exercises for you, so we'll get to interact then as well. Okay? All right, so we're going to talk about multigraded modules. We're not actually going to talk a ton about modules today. And the reason is that if we're going to talk about multigraded modules, we should know why. So that is what we're going to do today. And so the main reference would be in Cox-Little-Shank's Torque Varieties book, section 5.2, not the whole book because it's like this thick. Don't do that. But a lot of things are kind of roughly from there and like previous things they reference in that section, if you want to be able to look at a text to go with it. So what I first want to do, I'm sorry, I'm like recovering from allergies, so I promise I'm not sick. This has been like 10 weeks in the making. So I might cough periodically. Okay, so the first thing I want to do is just briefly recall some things you've heard last week and even this morning about projective space, right? And then we're going to move beyond that, so as motivation. Okay, so first, let's let C be an algebraically closed field. Because I'm going to write C, but it doesn't actually matter what the characteristic is. All right, so when we're working with projective space, so Pn, we saw, right, we should take n plus one dimensional affine space, remove the origin, and then quotient by an equivalence relation. I'm going to call this C star instead of tilde, where because C star is acting on C to the n plus 1, right? And the equivalence relation is just asking for the orbits of that action, right? So here we're saying lambda acting on a vector x is lambda x0, lambda x1, lambda xn. Yes? I'm hoping this is close enough to what I saw what Adam did this morning, that this feels okay. All right? Okay, and of course, then the thing when we're quotienting, the thing we're doing is we're looking at lines through the origin, right? Those are our orbits, just scalar multiples of a vector. So a line through the origin minus 0, and that single line up here maps to a point here. Okay, and let's just let pi be that map. So I have Cn plus 1 down to Pn, and so pi will just be my quotient map. Okay. So now, all right, we have the algebraic geometry or ideal variety correspondence. Which Claudia told you about last week. And so on one side, we have closed subvarieties of our projective space. And these are in one-to-one correspondence with our homogeneous radical ideals I that live inside of, oh, I didn't fix this notation yet. All right, a couple things. Let's here write, okay, let's see. So S is going to be our polynomial ring. All right. And then M is the homogeneous. Oh, can I not write that low? Sorry. That makes sense. I was thinking about that. Let me do that. I'll squeeze this in. Hopefully this is standard notation. So M is just the ideal generated by all the X's inside of S. So this is our maximal ideal. Question?
Minor detail. What does pi do to 0?
Oh, sorry. Thank you. I meant to hit -0. There we go. Good, good. Okay. All right. So here, I'm going to take an ideal I, and I'm going to send it to what I'll write like this. And this is relevant because now I want the pi of p's. So these are things in my projective space such that f of p is 0 for every f in I. And then vice versa. To go back, I just look at the collection of points I'm considering and ask for all of the polynomials that happen to be zeroed out by those points. Okay. So far, so good? Okay. So next, definition. All right. Yes. Cover up that. You got it? Oh, sorry. Here. Go way up. All right. I will keep that in mind next time and not do that. All right. So, all right, a minimal free resolution is, and I'm doing graded here too. I should say grade, everything is graded, so I'm not going to write it down. Is a complex F oh, and I did it. Okay, such that each Fi it's like this. Remember, we call these numbers, these ranks, Betty numbers. Okay, and my homology is 0 for all I greater than 0. Should I define homology? I'm seeing lots of no's. Are there any yeses? Are there some yeses? Should I define it? No? Okay. All right. So, right, and then it's a free resolution of something, and the of something, the something is the 0th homology here then. Yes? Okay, great. So, example. I wrote this down ahead of time. I cheated. Twisted cubic, right? So it's a curve inside of P3. Oh, question. Oh, thank you. Yes. Yes. And one more and. I didn't write these down. The image of partial I. So in other words, if I fix bases and write down matrices, I don't have any units in my maps. Okay, so twisted cubic, one way to present it is cut out by these 3 equations, right? And so a few features here, right? I have 3 equations, so I have a rank 3 thing here. They're all degree 2, so that's why this is rank 3 with a -2. So the -2 is keeping track of degree. As a reminder, these are linear forms, so my -2 gets shifted back to a -3. And I have 2 columns again, so this is a 2. This is a really beautiful resolution for many reasons. One thing that's cool, being length 2, this is an example of a Hilbert-Birch resolution. And so, in fact, these 3 equations are the 3 minors of this matrix. So one way to think about these is if you just, all right, if you repeat, well, maybe that's enough. But yeah, if you repeat columns here, you can see the syzygies happening. But I'll leave that there. All right, so we're almost done with our review. So the theorem I want to highlight today is Hilbert's syzygy theorem. So this is very classical, 1890. Okay, and I'm going to state it in a specific way. Okay, so if I have a subvariety of Pn, and then I let I of x inside of S be the ideal of x. Okay, so when I say the ideal, I mean the radical homogeneous ideal associated to it, right? Then the minimal free resolution of S mod I of x has length less than or equal to n. Okay. This n is this n, which is the dimension of projective space. So that's what I want to highlight here. All right. And so this is one instance of being able to like see a geometric invariant getting involved with the homological algebra on your space, right? And this is like one small way. In fact, the reason Hilbert proved this theorem was he was looking at proving the existence of Hilbert polynomials. He did that in the same paper, right? And the way he did it was by computing Hilbert functions through the minimal free resolution and using an alternating formula, right? So that if I want the Hilbert function of this in a certain degree, I can just take degrees here and then take dimension of each graded piece in an alternating sign format, okay? In order to do that, you need to know that this stops and doesn't go on forever. Otherwise, you'd be adding and subtracting forever and ever, and it may not end. This told him it stopped, and so he got the existence of the Hilbert polynomial from this complex, okay? All right, so in fact, from this theorem in the paper therein, we're seeing, the Hilbert polynomial contains more refined information about the dimension of x, its degree. So inside of free resolutions already, we have dimension and degree. It turns out there are a lot more things you can see inside of the syzygies, the free resolutions, in as far as geometry goes. Okay, so I could spend a whole semester just talking about that, and I want to talk about something else. So Eisenbud's Geometry of Syzygies book. If you haven't seen it yet, I definitely recommend it. It's really beautiful. All right, so this tells the story for projective space about how to pull all kinds of really beautiful geometric information out of free resolutions in this standard graded, like usual homogeneous case. All right, so this is for PN. All right, but we want to do multi-gradings, and so we are not going to focus on this. Next time I will tell you another theorem. Last week you talked about the Eisenbud-Godot linearity theorem. We'll revisit that and think about that in the multigraded setting. But kind of the idea of a lot of research I've been doing is thinking about how to take things in this vein and transport them to multigradings or other settings. And so I want to explain sort of why we might want to do that. Let me see. I am going to keep this for now and go here. All right. So let me tell you, when I say multigrading, what I mean. Actually, no, it'll fit here. Okay. Okay. So now I'm going to keep using S for my ring but I'm going to drop x0. Help me remember that's a capital N now. All right, so a multigrading. So a multigrading on S comes from an assignment where we're just going to define the degree of each variable to be some vector now in z to the d. Okay, so I'm not going to write vector symbols on everything or I'll be here all day. So this is now a vector. And this is the key, right? So for projective space, these were ones in Z, and now they're going to be something else. All right, our first example is for P1 cross P1. If I wanted to work with P1 cross P1, well, what am I doing? I'm now going to take a C2 and a C2. I'm going to remove the origin in each place and project down. That means I should be keeping track of degree here for homogeneity and keeping track of degree here for homogeneity and doing that separately. So the way I'm going to do that is by using x's and y's. And I'm going to let the degree of my x's be 1 in one coordinate of Z2. And then my y similarly in the other coordinate. So I'm keeping track of them independently. So for instance, if I wanted to look now, I'm looking for bihomogeneous equations, right? So one graded thing here. So I'm going to write down something that's homogeneous. So I can do like, I'm going to write something down of degree 2, 2, okay? Let me see. I tried to give you all the different options that can go together here. So this has degree 2, 2. Yes? Because I have 2 x's and 2 y's in every monomial. That's it. Okay, so this is our first example of multigrading. It's not super exotic, but it turns out to be quite useful and like shows up in real life, right? There's often times where we're going to have 2 sets of variables that are going to be independently have homogeneity conditions on them, right? Or maybe more sets and just be looking at other products of projective spaces. So that certainly falls into this land. All right, so what I want to do is now give you sort of a combinatorial setting in which to think about all of these things. So we're going to like go back to projective space for a second, and I'm going to give you a way to think about them that goes in line with this Cox-Little-Shank setup, and then we'll circle back to P1 cross P1. Okay. So all right, so for projective space, what do I have? I have 3 variables that all have degree 1. Yes? So I could use that to write down a map like this, and then I could turn it into an exact short exact sequence, find its kernel, and this is what I get. So you can multiply matrices and check me. If you really want to get fancy, you can actually do the linear algebra. Remember, you're working over Z, but here it's okay. All right. So this is for P2. Okay, so this was my degree matrix. here. And then I just found this. Okay, so now I'm going to take these 3 rows and turn them into vectors in the plane. Right, so I have -1, -1. I have 1, 0. And I have 0, 1. Okay. And now I'm going to think about those on the plane and actually think about like their positive spans. Right, so this thing right here, I'll use. Right, this is like r greater than or equal to 0 times these 2 vectors. Right, all non-negative real sums of these 2. And then over here, same thing, these 2 vectors, and then I have down here. Okay. All right, so that's a thing we can do. Let's play the same game with P1 quickly. So here, now I just have this. This one's more degenerate. Just looks like this, right? Because I just have 2 variables now, x0 and x1. They both have degree 1. So my kernel is just the vector spanned by -1, 1. And so now I'm in on the real line. And I just have that. Yes? Question?
What is this exact sequence?
So this is, I'm just taking the degree matrix and then I'm just figuring out what goes here. So like the kernel of this is this. And I'm just telling you, I just computed it ahead of time. Okay. So yeah, so the procedure was start with the degrees, compute the matrix that is its kernel, and then use that to put down some rays. And then like, right, I put down these vectors and then I just like took these non-negative spans. Okay. So now let's do this. Oh, did I not? I didn't use my bottom board. Sorry, I wanted to reset. Okay, so with this in mind, let's go back to P1 cross P1. So I have my degrees there. I know what I want them to be. So let's work backwards. So now I have Z4 mapping to Z2. And now I have the degrees of my 2 X's and the degrees of my 2 Y's. Okay, I'm going to get these in the right order. Apparently the order I put them in. Okay, so I get this. Right, so this looks like a plus sign, where these are all unit vectors. And so then I can just fill them in. And so now this gives me a combinatorial object I could associate to P1 cross P1. And that is what we will do. Let me remind you now, right? This matrix is telling us what our action was that we quotiented by, right? So here, same thing. So now I can think about P1 cross P1 as taking C4 and removing something, right? I need to remove the origin from the 2 different C2s. So what is that? It's going to be the variety of where the X's are 0 and where the Y's are 0. So I'm taking this whole thing and I'm going to quotient now by a C star squared action. We're here now. This action is now, I have an S and a T acting on, I'll write out all my coordinates, this, and the S's are going to scale here and the T scale here. Okay. All right, so here's the cool thing. I can get this ideal from this picture. Okay, so I'm going to label these corresponding to this. So this is x0, x1, y0, y1. I'm just going in order here. All right, so this ideal equals, maybe I'll come back to it. I'm going to tell you the general thing and then I'll tell you how to, then we'll compute it using what I tell you so that it's not a mystery. All right, so what is this object? This object is called a fan, and I'm just going to briefly define what that is. Our fans will today on the board will be in 2 dimensions, but you can certainly do this in higher dimensions as well. Okay, so a fan sigma in Rn is a finite collection of cones, right? So these cones are these non-negative spans of some vectors. All right. Such that a bunch of things happen. And I'm going to give these to you not super precisely, but in a way, hopefully, that makes this quick to just understand that it's the thing it should be to like mathematically be a useful object, right? So first, well, I should say cone sigma. Every cone sigma, right? All right, maybe I'll write, this one is easier to just write down. Oh no. Oh yeah, this is how I want to say it, is contained in some open half space. Okay, in other words, I don't want to have 2 vectors that point in the opposite direction inside the same cone, because that kind of messes things up. Okay. Every subcone is a cone in sigma, right? So in other words, sigma is closed under taking subcones. And when I say subcones are always generated by subsets of these vectors, right? It's the only thing that makes sense. Okay, and then it's also closed under intersections. So cones in sigma are closed under intersections. Right, so if I take 2 cones and I intersect them, I get another cone. So in our picture here, maybe I'll use this one since it's down lower. Right, so I have 3 maximal cones, 3 2-dimensional cones. And if I intersect, say, the orange and the pink here, I get this 1-dimensional cone. I'll call it, right? It's just the non-negative span of this one vector. And if I intersect with anything else, I'll just get the origin. So like the origin is, right, the non-positive, or sorry, the non-negative span of the origin is just the origin, right? And so forth. So 3 maximal cones, in this case, 3 1-dimensional cones, and then, this single 0-dimensional cone, which will always be the case because of, right, so there's always just the origin. Right here, I just have 2 1-dimensional cones and a 0-dimensional cone. Here, you're seeing 4 maximal 4 2-dimensional cones, 4 1-dimensional cones, and 1 0-dimensional cone. Yes? Okay, so this is the object we're going to work with. All right, so just 2 more things. So the support of sigma is just the stuff in R to the n that has a cone living over it. Okay, so this is the, I want to write it like this. You can also do this for just a cone, and it's just the union of the actual points in Rn. Okay, so here I'm really just thinking about the points in Rn. So like the support of this fan is all of R2. Okay, and then the other one, so sigma of R is the R dimensional cones. So if I write sigma of 1, oh, sorry, that's the wrong way. If I write sigma of 1, I mean the rays. That's what we're going to use the most. Okay. All right, when we look at cones, we're always going to assume they do this, right? So we're going to restrict to all cones being generated by sets of linearly independent vectors. Okay, so this condition is called being simplicial. Okay. All right. So from this, now I can define sort of the generalization of this picture. Okay. Oh, let's do that here. So let's let sigma be a simplicial fan. And now it's going to be in Rn. Oh, sorry. It can be an R anything. The important thing is I'm going to set little n. What do I do? Capital N. Let's set this to be the number of rays. So this is in some R to the something. All right. So what I want to do is right, this capital N is going in the middle of my sequence. Question?
Yeah, I just want to make sure notational clarity. For me. So when we do the bars on just sigma, that means the support. But when we take bars on a particular thing, that means the number.
Good question. So yes, sigma of 1 is the set of rays. Yeah. And so then I'm taking the cardinality of a set.
Yes.
Great. Yeah, this is a good clarification for notation to make clear what different things are. I love it. Anything else? You could, but you could like choose a cone, like in R3, you could choose a cone that's like the span of things that are not linearly independent, or you could pick like 2 vectors that are on the same. So you could pick something like this, or you could pick like 2 vectors that are on the same, that are, you know, dependent. Or I could pick like, if I picked something that was in here too, I don't want to pick that. So I'm really excluding. I want to carefully choose these so that they're actually linearly independent. What's that? Well, so the point is that the generated by, what am I actually considering a ray versus what's just in the span? Okay, so like over here, I just had, like for this 2-dimensional cone, that's this first orthant, the generators are these 2 standard basis vectors. Like if I picked something else in the middle, I don't need that to generate the cone. I don't want to include it. Okay, great question. Okay, so what I want to do is I'm going to put the rays of sigma as the rows now of this matrix. Right, that's what we did in our 3 examples so far. And then I'm going to get a co-kernel over here. And I'm going to use this to give me a grading on S, where now S is right. In order for this to make sense, I need the columns here to have capital N of them. So this is my ring. Okay, I should say, right, so here columns correspond to variables. All right, and I should have let me give myself a little more space so I can fit one more thing. All right, inside of here, I'm going to choose an ideal that's going to be generated now by what we usually write as x to the sigma hat, which just means the product. So each ray I can think of as corresponding to a variable just by index. And so I want to pick the things not in some cone sigma and multiply all of those together. Okay, and maximal cones here is enough. When I do that, all right, well, let's go over here. Let's compute what that is here. Okay, so I'm going to go through my cones. And I have here x0, y0. So the things not in are the product of x1, y1. And then I have this cone. So the 2 things not in there are the x0, y1. And then moving 3rd quadrant, so I have x0, y0. And then 4th quadrant, I get x1, y0. And lo and behold, you can double check that these are equal. Okay. All right, so that is what this process is doing. You just can go around. Yes, Adam? Yes. Thank you. Yes, this should be a D or this should be a K, either one. I've been using D. Okay. All right. All right, so a simplicial toric variety now associated to the sigma is x, or x sigma is now, I'm going to take my c to the capital N. I'm going to remove the variety inside of c to the capital N of this ideal B. I take this whole thing and I quotient now by a C star to the R action, which is exactly the thing given by the columns of these. Right? So if you look here, C2 corresponds to this degree matrix right there. So this is the general formula. This is a lot to parse. This is why we have exercises. So I'm hoping you understand the examples right now. I do not expect that this makes a whole lot of sense if you haven't seen this before, and that is okay. So you will have time later to puzzle through it. And in fact, you can actually do most of the exercises just thinking about products of projective spaces. So things that look like that. All right, question?
Going back to your exact sequence of lattices, should I be thinking of them as sets of row vectors? Like Z to the D?
This.
Yeah. So I think of that as row vectors. So that like 1, 0, 0 maps to the first ray, which is a row vector.
I would think about these as column vectors. Like these are column vectors. So that then I'm taking D. Yeah, I'm choosing like Yeah, I have the rows here are row vectors, but then they're turning into column vectors. Like these things are columns in the end.
So like the image of the column 1, 0, 0,
Right.
0 is
Goes.
the first entry of each ray.
Yeah.
Okay.
Yeah. Yes. Absolutely. And this is the key. Yeah. So the comment was there are a lot of simplicial torque varieties that aren't products of projective spaces. And yes, that's exactly right. And the point is the same machinery applies. So we can just do products of projective spaces and get a lot of bang for our buck and get really cool, beautiful math. But like sort of the same things we're doing apply in this broader context. Right, I want to give you one quick example that isn't a product of projective spaces, just so you can see what that looks like. It's actually a P1 bundle over a P1, which if that means nothing to you is totally fine. So this is the second Hirzebruch surface. Okay, and here the fan looks like this, right, where now I'm going to go around like this so that my short exact sequence looks like this. Okay, and so my rays are, oh, sorry.
Going back to the board above, did you say what the action was of C star to the R?
Yes, this action, so this is given by this DEG matrix, or this is essentially DEG, the matrix telling the degrees. Right, and that makes sense, because what's happening then is it means if I, just like we did in projective space, if I take a polynomial that's homogeneous here, and I multiplied through by my action, I should be able to pull out that monomial. Actually, I was going to say that in just a second. It's on my next sheet. That like here, if I took f of x and then I put a lambda in everywhere, like lambda to the degree pulled out, now I'm going to get all of my variables to the right multi-degree will pull out. So I'll get like, you know, each variable in for C star, each coordinate will have the correct monomial corresponding to that degree vector. Okay, right, in particular, like for P1 cross P1, I scale my x's by one thing, my t's by something, I'll get s to the x degree, t to the y degree pulling out of my polynomial. That?
Yeah, I think so.
Okay, yes. Oh, so the word toric is coming from torus. The algebraic torus is just C star to the something. It's a deformation retract of a product of S1s. So like, as algebraic geometers will say, like what we call a torus is not the same thing as topologists, but they're retracts. Like one is a retract of the other. Okay, so the word, like we're not actually going to do anything with like tori per se, but algebraic tori are showing up everywhere. Let me finish this. So -1, 2. All right, so these 4 vectors are meant to be those 4 vectors. And then the thing that I get here looks like this. All right, so now for the multigraded commutative algebra I want to do here looks like this. Oops. Oh, I am using, sorry. I'm switching back to zeros. I apologize. Macaulay 2 uses zeros. I didn't use zeros up here. But right, so the degrees are this x0 has degree 1, 0, x1 has degree -2, 1, x2 has degree 1, 0, and then here I have 0, 1. All right, so you can secretly see there's a P1 sitting inside of here again, right? And that corresponds to now these are my P1 variables, and then I have these 2 other variables that have this funky extra thing, and that's where this, you kind of have a P1 with like a twisted P1 living above it. Okay. All right, so there's 2 more things I want to tell you in 5 minutes. I can do it. All right, now I can go ahead. Yes. Oh, yes, yes, yeah, absolutely. So here, so I have acting on C4. And so I have like ST acting on a vector X. And so now S is going to scale X0 because I have a 1 here. So I'm going to use this as an exponent vector on S and T. So here I have S to the minus 2 T to the 1 times X1. And then I have S times X2, again to the 1, and then just T to the 1 because there's just a T there. Does that help? Okay. So these have come from this underlying torus action. There's a beautiful story. There's all these cool things about the orbits and the cones, and like that was a whole nother multiple lectures. We could just do that this week, but we're going to talk about multigraded modules instead. But I'm happy to chat about that later if you'd like to see more pictures. All right, so we had our ideal variety correspondence, and we still do. Okay, so now I have, what do I want to, yeah, let me do this. Okay, so now I have closed subvarieties of my simplicial toric variety X or X sigma. So there exists a one-to-one correspondence here with now homogeneous radical ideals that live inside B. Okay, so we still have a dictionary where I can take ideals here, get sets of points, right? And I'm just doing the same thing we did for projective space. I'm going to kind of pretend that I live up here, but then because everything's homogeneous, if I vanish at one point in an orbit, I vanish at everything, and so it will pass down. That's why we want the homogeneity. Okay. And there's an exercise to prove the following using usual Null-Selensatz. No, oops. There we go. Okay. So, all right. So I in S is a homogeneous ideal. Right. Then, right, how do we know if the variety of I is doing anything geometrically? This will be the empty set now of my variety. It matters where I'm considering varieties. So here I want to think about my variety inside of X sigma, not upstairs in C to the capital N. Okay. And the answer is that some power of this B, right, which I should say here, I'm going to call this the irrelevant ideal. Some power of this irrelevant ideal lives inside your ideal, right? That forces essentially your variety to only involve points that we took away. And so there's nothing that lives down in X sigma. Okay, yes? Yes, for some, thank you. Talking and writing at the same time are not my strong suit. There you go. Okay, so that's one thing to investigate, yes?
What exactly is the definition of X?
Ah, this. Okay. So, all right, I'm going to take one extra minute just so I can say this last thing, okay? We had free resolutions for projective space, right? If we now look at minimal free resolutions over something like this, right? If I resolve say, some points, or even for P1 cross P1, I have an example here. I maybe won't write it down for time. If I take an ideal of points inside of P1 cross P1 now, that will have length 3. The dimension of P1 cross P1 is 2, right? So we've already lost like the niceness of Hilbert's syzygy theorem in that sense, right? But maybe we're looking at the wrong object. Okay? So the thing we want to do instead now is allow ourselves a little more wiggle room when computing homology. So a virtual resolution is now, we still want minimal. So a minimal free complex, of course graded, now multigraded, with, just write it, right? Each HI of F is now B torsion. Right? What does this mean? This means that, let me get this the right direction now. The annihilator, I always get this backwards. The radical of the annihilator should contain the irrelevant ideal. Okay? For projective space, right? For projective space, this isn't asking anything because the irrelevant ideal was the graded maximal ideal, the ideal of all the variables. So like minimality sort of already forced this to happen. But once we move to this more general setting, this B ideal is going to be deeper into the ring than the graded maximal ideal. Okay? So one way to get something like this is to just take your original, the ideal you're interested in, right? For instance, in your ideal variety correspondence, just an ideal generated by homogeneous forms corresponds to a subvariety. You want to know some geometry about that subvariety. You can't use the syzygies in the minimal free resolution, but you could just take that ideal, intersect it with this. That would be introducing B torsion at the H0 level. Just resolve that. And that would already be giving you something. And sometimes you can get shorter just doing that. So that's some of what you'll do in the exercises, is just start looking at ideals that are homogeneous, intersecting with B or components of B, so that you're introducing some of this B torsion and seeing if you can get resolutions that get shorter, so that you can maybe get down below the dimension of the space at least. Okay? I will stop there.